In this video, I want to discuss with you another source of energy that can be used to drive reactions. This source of energy is called entropy and is often labeled as delta S naught. The little naught or zero sign just means that we're dealing with standard conditions. And in the grade 12 curriculum, we only deal in standard conditions. If for a moment we consider the main source of energy from our last lesson on enthalpy. Remember from our energy diagrams, enthalpy was my delta H. Enthalpy talks about the heat that might be released in a chemical reaction. In this case, the reaction was exothermic. We knew that energy needed to be added to the reactants, we called that the activation energy, in order to get to the activated complex, the point where the bonds broke and could be remade. But once that reaction happened, all of this energy was released and could be used to kick the next set of molecules back up to the top of the hill. The energy that was constantly being produced was enough to be able to continue to drive the reaction forward. How then can we make an endothermic reaction happen? Well, I might initially put in a large amount of energy to get to the activated complex. The products will keep most of that energy trapped within their bonds. No energy is being released in order to drive the next two particles back to the top of the hill. In an endothermic reaction, what makes the reaction go? The answer is entropy. Entropy is best described as randomness. Anytime something becomes more random, energy is released. Consider a box full of marbles. If we spill that box, does that release or take energy? Well, your first thought might be that requires energy. In fact, you had to tip the box over in order to spill it. But think about the reverse reaction. Now I want you to pick up all those marbles and put them back in the box. Oh, well, here we know that in order to put all those marbles back into an organized system, become less random, that requires energy. To organize requires energy. To allow things to spread out to disorder, to become random, then must release it. What is true in one direction has the opposite in the reverse reaction. In all physical and chemical systems, things tend to move towards states of maximum disorder. It's a consequence of the Big Bang Theory, that as the universe continuously spreads out, a fixed amount of matter necessarily becomes more random. Entropy must increase. So we know then that entropy will increase anytime we watch a chemical reaction and notice that the physical states change from solid to liquid or gas. Solid being the most organized physical state of matter, and a gas being the most disorganized. We can also look at the number of individual parts or moles of product and reactant. Entropy also increases as we divide into smaller and smaller parts. If I see a decomposition, for example, reaction, where one thing breaks down to two or three things, it has necessarily become more random and entropy has increased. We also note that entropy will increase anytime the temperature increases because the particles become more chaotic. Anytime entropy is increasing, energy is being released that can make a reaction tend to go. So a positive change in entropy favors a chemical reaction going, and a negative change in entropy requires energy and often favors a reaction not wanting to go on its own. What then would be the best case for a spontaneous reaction? Well, a spontaneous reaction will always go when my enthalpy, my delta H, is a negative value. This means heat energy is being released, and that energy can be used to provide activation energy. And when my delta S is a positive value, it's becoming more random. So if my reaction is both exothermic and positive entropy or more random, I will always have a chemical reaction occur. What then would be the worst case for a spontaneous reaction? Well, when my delta H is positive, in other words, is endothermic, then we must be adding energy constantly. And if my delta S is negative, in other words, it's becoming less random, this would also require a constant input of energy. In a case with an endothermic reaction that becomes less random, these reactions never go on their own. They will only go if we are constantly finding some source to input energy. What if we have the scenario, however, if my delta H is negative, it's exothermic, and my delta S is negative, it's becoming less random? Or what if my delta H is endothermic, which requires an input of energy, but my delta S is becoming more random? Well, in these cases, it depends on how much of each we have, and it can be calculated by using Gibbs free energy calculations. We don't go into Gibbs free energy calculations in grade 12, but the calculations are simple. And the answer is it really depends on the temperature that the reaction is happening at. It is a simple set of math calculations, but it's not in our curriculum. So if you're interested, you can read about it in your textbook. Otherwise, we'll consider these situations as it depends on the scenario. To read more about entropy, you can find questions in your textbook in chapter 15.5, and you can work on questions 48 through 50 and 95 through 97 on pages 548 and 553.